Okay, so in this lecture, we briefly talk about calculating the invariant factors of a given matrix. Okay. First thing is recall a few things that if you have a finite dimensional vector space, let's say, suppose V is a finite dimensional vector space, and you have a direct sum decomposition of V. It's a invariant direct sum decomposition of V, let's say, and you have a linear operator defined on V. Let T be a linear operator defined on V. Okay. Then recall that if you restrict this linear operator to each of these invariant subspaces, because if you define Ti to be the restriction of T to Wi, I ranging from 1 to k, okay, then you can write T as a direct sum of these linear operators. Right? What is the analogous point of view from a matrix? If I say so, if I choose a basis, from of each of these Wi, so let's say Bi is a basis of Wi, then you obviously have a certain matrix representation of this linear operator Ti with respect to Bi, and let's say that's basically Ai. Okay. Then if you recall that if you form a sequence of these basis elements according to the the subspaces, the T invariant subspaces you have, then you get an ordered basis for V. Right? So if you arrange this like B1, B2 until Bk, then this forms an ordered basis of V, right? So this should be an ordered basis. It's an ordered basis of the ordered basis for, I should use the term for V. Okay. Then what is the matrix representation of T with respect to V? If you quickly recall, then this is basically the direct sum of each of these matrices AI, right? So it's A1, A2, so on till AK, right? Each of these AIs, they are sub DI cross DI matrices, where DI is basically the dimension of WI, right? And this is pretty obvious to follow, because how do we calculate each of the column spaces? So they basically come from the image of each of these basis elements BI, right? So this is very easy to follow. Yeah. Now, if you recall the concept of the cyclic decomposition of a finite dimensional vector space, so let V be a finite dimensional vector space, and T is a linear operator on V, then what does the cyclic decomposition say? That there exists non-zero vectors alpha 1, alpha 2 till alpha r with respective, so these are the elements from V with respective T annihilators, right? With respect to T annihilators, which we had named as P1, P2 till PR, such that you can have a direct sum decomposition of V in terms of a T admissible subspace W0 and the cyclic subspaces, the T cyclic subspaces generated by each of these non-zero vectors, right? So you get this, right? So this is merely the cyclic decomposition theorem, and it also speaks about this representation being unique in terms of R, the integer R, and these T annihilators. And obviously, what is the, let's say the dimension of the T cyclic subspace generated by alpha I, the Ki. Suppose Ki is the dimension of the T cyclic subspace generated by alpha I. Then by the definition of a T annihilator, what should be the basis of this cyclic subspace? This basis we also call it to be the cyclic basis. If you recall, we also say it to be the T cyclic basis, to be precise. We call it to be the T cyclic basis. Then the T cyclic basis, the T cyclic basis for Z I T So this basically comes out to be alpha I, t alpha I, I mean t of alpha I, and so on till t to the power ki minus 1 of alpha, right? This is pretty trivial. One more thing which we can observe, because Ti by definition of a Ti annihilator, so is the least degree monic polynomial such that it annihilates the vector alpha, right? So what should be Ki? So Ki is basically the degree of Pi, right? It's the degree of Pi. Recall one more fact which we had come up while proving the cyclic decomposition theorem. Oh, okay. Well, there is one more statement from the cyclic decomposition theorem which I missed, that is that Pk plus 1 should divide Pk, right? Pk plus 1 should divide Pk. Yeah, this was an important fact of the cyclic decomposition theorem. I missed it. So also one more thing which we had got from the proof of the cyclic decomposition theorem was that P1 forms uh, it forms the minimal polynomial of the linear operator T, right? If you recall, right? Okay. So, yeah. So this is the T cyclic basis for Z alpha IT. Each of these Z alpha ITs are T invariant subspaces. W naught is a T admissible subspace, so it's also a T invariant subspace. So this is a invariant direct sum decomposition of V, right? Therefore, we can apply this observation directly to it. So if you choose this to be Bi, and if you restrict this T to each of these T cyclic subspaces, okay, then what happens? Then you will get a matrix representation of Ti with respect to Bi. You can name it as AI. What should be AI? Then recall AI is the companion matrix. AI is the companion matrix. Now, this is pretty obvious. The first lecture we had on the cyclic subspaces, recall that if you restrict a linear operator to a cyclic subspace, then the T annihilator of the vector which generates that subspace comes out to be the T annihilator, comes out to be the so the matrix representation is given in terms of the companion matrix of that polynomial, right? So what I'm trying to say is that recall this. So if you're a linear operator in terms of what we have discussed here, if you restrict T to some Z alpha T, okay, let this to be T alpha, let this to be T dash, then T dash has the minimal polynomial, P alpha. P alpha is the T annihilator of alpha. It's the T annihilator of alpha. Okay. Then this matrix is nothing but the companion matrix of P alpha. And in this case, that is the companion matrix of the vector alpha I, right? So it's the companion matrix of Pi, because Pi is given to be the T annihilator of alpha. Right? So Ti is basically the restriction of T over the T cyclic subspace generated by alpha I. So Ai is the companion matrix of the T annihilator of alpha I, which is Pi, right? It's I guess it's clear now. Okay. So what should be the dimension of this matrix Ai? So it should be the dimension of the of the degree of Pi, right? So let me just write it down here. So Ai is a matrix Ki across Ki, where Ki is typically the degree of Pi. That's quite obvious. Okay, so it's the companion matrix of Pi. I guess it's clear now. So then we go by the analogous terms that if you form a sequence of these basis elements B1, B2 till Br, obviously Bi is an ordered basis. So B forms an ordered basis arranging in a similar sequence. So what is T of B? Then T of B simply forms a matrix A1, A2, AR. Each of these AIs are companion matrices of the respective T annihilators, and this matrix is what we call the rational form, right? Is what we call the rational. Okay. So to calculate the rational form, what we need is basically the respective T annihilators in order of the cyclic decomposition of the given finite dimensional vector space. So that's what we all we need. Let's now come to few facts about it. Okay. First thing first, we can consider this as an observation. You might say that suppose you choose the companion matrix of some given polynomial, monic polynomial. So let P be a monic polynomial x to the power n plus Cn minus 1 x to the power n minus 1 and so on and so forth till C1x plus C0. Okay, what is the companion matrix of this? We know, I'm not writing it down. Okay, let's just write it down. So it's very simple. You have just 0 1, all the elements are 0 here, then you have 0 0 1, elements are 0. It continues to the second last column, but the last element is 0, and the last column consists of these coefficients. So it's minus C0, minus C1, so on and so forth till minus Cn minus 1, right? Okay. So then what should be the, so suppose this is A. Suppose this is A. Then what should be the matrix xi minus A? Then this is typically the matrix x minus 1, all the elements are 0. Then you have 0 x minus 1, all the elements are 0, then so on and so forth till you have, here you have x minus 1, right? And the last column you have here C0, C1, so on and so forth till x plus Cn minus 1, right? Right? Okay. Now we do a simple process. What we do is that we add x times row n to row n minus 1. We add x times row n to row n minus 1. Okay. Okay. What will this do? This will remove the x from n minus 1 comma n minus 1. Clear? So if you have a row n, then just below it you have minus 1, right? Suppose you choose this. Suppose you choose this row. Okay. So if you add, sorry, if you multiply minus 1 x to this row, then you get a minus x term here. You add it to the previous row. You are adding x times Rn plus Rn minus 1, right? So you are adding x times minus 1 to the previous row, right? So minus 1 times x plus x will cancel out the x in the previous row. Guess it's clear, right? Okay. But it won't change the determinant. These are simple row operations. It won't change the determinant, and we continue this process. That what we do is that after doing this, we multiply x times the Rn minus 1 to Rn minus 2, and we continue the process. Okay, we continue the process. As we continue the process, we reach this matrix. If you carefully observe, we reach the matrix of the form 0 minus 1 0, all the elements are 0 here. Then you have 0 0 minus 1, all the elements are 0 here, so on and so forth till you reach this matrix, this element x to the power n plus c n minus 1, x to the power n minus 1, so on and so forth till you have c1x plus c0, right? Below it you have just one degree less, so you have x to the power n minus 1 plus c n minus 2, x to the power n minus 2, so on and so forth till you reach here c1, right? And you continue in this process. The last element you have is x plus cn minus 1, right? You have in the previous row, I mean in the second last column, we have minus 1. So these are the columns. So I thought I misspelled it to be row. So, got it? Determinant of this is same. Also observe that this is nothing but the polynomial we started with, right? Okay. The determinant of this should be same as this. Right? We are using simple row operations. Right? We are not interchanging. We are simply using the addition. Some multiple times a row plus another. We are using that operation typically. Okay. Now what we do is that we simply eliminate all the elements in the last column, leaving the polynomial p. Only leaving the polynomial p. Okay, this is the polynomial p, right? We just remove this part and we simply write it to be p. So this is nothing but p. Right? This is very easy to do, right? You can just clean up the last column by adding to its appropriate multiples of the other column, right? You can just multiply with some x here, then add it to this. You will remove that x term, then you multiply x squared to this and add it to here. You will remove the x squared term and so on and so forth. So what we do is that adding to the last column appropriate multiples, what we are doing is basically, so the last column, let's say it's Cn. So what we are doing is Cn plus some power of x to the power I, let this to be capital Cn. Okay. Because the other coefficient, we have used the coefficient as here, so let this be Cn plus some Ci times x, and we can remove it, right? Okay. Ci times xi of the column, whatever column you choose, it's capital C. Okay. Yeah. So, yeah. Cj, just let me just write another index. Yeah. So adding to the last column appropriate multiples of the other columns, right? This is precise. Doing this, what we get? We get this matrix. We get the matrix 0, minus 1, 0. All the elements are 0 here. We get 0, 0, minus 1. All the other elements are 0 here, and so on and so forth. We continue. We have 0, 0 till you have minus 1 here, and the last column is nothing but p, and all the other elements are 0. Right? Now what we typically do is that we multiply each of the first n minus 1 columns by minus 1. Okay. So multiply each n minus 1 columns by minus 1 and interchange the adjacent columns. Interchange the n minus 1 adjacent columns to bring the last column to the first column. To bring the last column to first. So how many total number of interchanges we had? We had 2 n minus 2 interchanges. Right? Interchanges. So determinant is typically unordered. Right? I should say not interchanges. I should say 2n minus 2 sign changes. I should say each column interchange brings out a sign change, and each multiplication by minus 1 brings out a sign change. So there are total 2n minus 2 sign interchanges. So it doesn't affect the determinant. Not affecting the determinant. Not affecting the determinant. Okay. And what is the new matrix we get? So we get typically this matrix. So it's just P, all the other elements are 0. Then we have 0, 1, 0, right? So on and so forth. The last column is 1, right? Then it's obvious from here that P is simply determinant of xi minus, which is the other way of saying around that P itself forms the characteristic polynomial. Okay. We are given a proof of this in some previous lecture, I guess. Okay. Also, one thing is to be noticed that you should recall, or I should say, you should keep this all these steps in mind. Let me just use a notation for this operation. for all what we did in this observation notation for these set of operations. Let's say, what should we use? Let's say theta. Okay, clear? Now what have we essentially done here? We have essentially taken the help of some row and column operation as we used to do in case of matrices over fields. Obviously this matrix which we worked with, which is the matrix xi minus a, this was not a matrix over a field, it was a matrix over the polynomial algebra. Okay, so let A be a matrix over the polynomial algebra. Let me just denote it like this. Okay, so we can also consider this to be having the name polynomial matrix. Okay, polynomial matrix. Now we know what row operations are. We know what row operations are for matrices over a field, or I should say scalar matrices. Let's say scalar matrices. Okay. So analogous to this, we want to define some row operations for polynomial matrices. Okay. But these things are obviously analogous with a slight change to it. We will obviously observe the slight change. So how can we define elementary row operation over or for E? Number one, multiplication of a row of A by some unit in F. Sorry, by some let's say by some non-zero scalar in F. Okay, that is all the constant polynomials over Fx. Number two, replacing the rth row by row r plus f times row s. Okay, where these are pretty obvious, right? Where r is not equal to s and f is a polynomial over f. Okay. And the last is also very obvious. It is the interchanging of two rows. Interchanging two rows. Okay. Now these tools are what we have already used. The first one is slightly different, and the reason is pretty obvious. We know that each elementary row operations gives rise to an elementary matrix. Or rather, let me not go in that direction. Each elementary row operation, for each elementary row operation, we can define an inverse elementary row operation. Right? That is, if we have made a certain change to a matrix using using a single row operation, then we can invert that to get the original matrix by just simply inverting the operation we had. That is, if I had row r plus f times row s, we can invert this to get the original matrix we had. To have that inverse, in case of the first point, if I multiply it with this any arbitrary polynomial f, then to have the inverse, we need to divide it by the polynomial f. So in order, we need to multiply it by the reciprocal of some polynomial. But this is no more a polynomial, right? This is not in fx. The only way the reciprocal of some element will still remain in fx as a scalar is only if f is a constant polynomial, right? Or f is some non-zero scalar. Yes, it's clear now? I'm not writing it anymore. Got it? And the other definitions are very obvious from here. That what is an elementary matrix? So it is an elementary matrix is the matrix we obtain by applying a single elementary row operation to the m cross f identity matrix. Definition: an m cross m elementary matrix is the matrix obtained by applying a a single elementary row operation by applying a single elementary row operation to the M cross M identity matrix. Okay, and the rest of the definitions follow obviously, because see, we can write one E of A represents a single elementary row operation. Okay, so this is typically the elementary row operation on I times A. Right? We can consider this to be a matrix again. So what we can say is that, so this gives rise to another definition which says that these are also pretty relevant, that two matrices are said to be row equivalent. So let M and N be matrices, M cross N matrices over the polynomial algebra. N is said to be row equivalent to M if there exists an invertible, if there exists product of uh, elementary matrices, say P, which can be written as E1, E2, Ek, such that N is equal to Pa, right? Because each elementary, so if this is suppose this is A1, then what is E of A1? So it is EI of A1. So it's EI, A1 was EI of A, right? So it's EI, no, I'm not trying to do this. Let me, yeah, so A1 is, yeah, it's EI of A1. And how was A1 defined? Let me say it like this. So this is, let's say, E1, and this is, let's say, these are two different. We have three elementary row operations defined, right? We have E1, E2, E3. These are the three elementary row operations we have. So E2 of A1 is E2 of I times A1, but A1 was, suppose this is first, it was E1 of I times. Okay. So this is one matrix, this is one matrix, and that's the way it follows. Clear? Okay. Obviously, if P can be defined in this way, then we can also define what is P inverse. So P inverse is nothing but Ek inverse, Ek minus 1 inverse, till E1 inverse. Right? These are pretty obvious. Problem comes in defining a row reduced echelon form of a matrix over a polynomial algebra. Okay. What we do typically is that, see, the problem here, what actually arises is that to make the leading non-zero entry to be 1 of the first row. Okay. Because we need to, so what we see, what was the procedure in having the row reduced echelon form? We used to have the leading non-zero entry of row 1 to be 1, and then we used to divide the coefficient, the element which was in the leading non-zero entry of row 1 by the rest of the elements. But that can obviously be a polynomial. The leading non-zero entry of row 1 can be a polynomial. So we cannot divide every other entry, every other entry of that that specific column with that element. Right? I'm trying to say is that suppose the first row comes out to be 0, 0, x, and blah blah blah. Suppose you have here A, B, and so on. Right? What we try to do is that we try to make this one. Right? How to make this one? We will divide the columns, the first column by 1 by x. I mean multiply it by 1 by x. Can it? This isn't possible, right? Sorry, very sorry. We are using row operation here, right? So you have x here, you have A, B here. This is some other matrix. So we need to make this x to be 1, and the procedure to do is that we need to, divide this by x or multiply this by 1 by x, but that's not possible. The row operation which we have defined is only we only have in hand the multiplication by some non-zero scalar, right? But to have some simple form, now like we know that row reduced echelon form was the simplest form, simplest row equivalent form. for a matrix, right? It was the simplest row equivalent form for a matrix. But we cannot use the row operations alone to have a simple form. Instead, what we do is that we mix up the row and column operations. Column operations are defined analogously. There's nothing different. So what we do, we mix the row and column operations. Okay. We mix the row and column operations, and then we come up with something which is called to be equivalent matrices. We no more use the term row equivalent or column equivalent. We simply use the term equivalent matrices. So two matrices are said to be equivalent. N is said to be equivalent to M. Let's say just equivalence. Balance. If there exists invertible matrices PQ such that N can be written as PMQ. This comes from the row operation. This comes from the column operations. You can think of it like this. Clear? Okay. So I guess we have introduced it fairly, how the matrices over the polynomial algebra work. The next lecture we will come up with great details over this topic. We won't be going through detailed proofs of this topic. We will be studying the theorems, and we will be studying how to find the invariant factors in terms of an algorithm where the steps in the algorithm are specific theorems. We will prove some theorems which aren't necessary, but we won't prove them all. Okay. So meet you guys in the next lecture.